Assalamualaikum warahmatullahi wabarakatuh. Hello everyone, here is with Alicia Naura Salsabila and my student ID is 432240103. I am in my fourth semester in the Robotics Engineering Technology study program. And today, in this occasion, I am presenting you my project for my Programmable Logic Controller course final exam for the scene 3 queue of items. So before we begin everything, basically in this project, the goal is to build an automatic queuing system where items get collected on a buffer conveyor and only get released once 3 of them has piled up. And in this, I am using Factory IO as the simulator and Modicon M241 logic controller to run the actual program. The next slide is for the program variable declaration. So in here, as you can see, the variable table that I declared inside the as our main program, and let's go through each one. First, we have an at entry with the address QX0.2 with data type bool for the entry sensor input, and there is a buffer with the address QS0.0 also that type bool, and then this is for the output that drives the buffer conveyor motor, and there is a CDU in where the data type is CDU, or it's for like count up counter block with no direct address, and it's a function block instance. This is for the CDU to count item that is entering the buffer. And also there is a CDU out which with data type CDU same as before, and another counter instance with also no direct address. This CDU counts items that leaving the buffer. And we have at exit with the address QS0.3 with also data type bool as the exit sensor input, and then we have a entry conveyor with the address QX0.1 with the data type bool and the output that drives the entry conveyor motor. So in total here, we have 4 of these that are simple bool signals with fixed IO addresses, and 2 of them is CDU in and CDU out. There are counter function blocks which don't get a single address because they are actually contain several internal values inside them. And next slide is the ladder logic for the conveyor control. So before I explain these rungs, let me quickly explain how I name things here. And this is basically from the standard. CDU or count up is a standard for IEC 61131-3 function block. CDU in and CDU out are the 2 instances of the function block that I declare here in my program. Each instance has its own inputs and outputs, like CU, reset, PP as inputs, and Q and CP as outputs. To reference a specific input or output that belongs to one instance, IEC 61131-3 use dot notation, where instance name dot then the output or input name. So it's like CDU underscore in dot Q refers to the Q output of the CDU in instance, and CDU underscore out dot reset refers to the reset input of the CDU underscore out instance. I'll keep saying the long spoken out the first version and put the actual name used in the program brackets after it. Let's see what is in the rung 1. In the rung 1, controls the buffer conveyor. It runs whenever the entry sensor, or it's called at entry, is inactive, or while the done output of the input counter CDU underscore n.q, the output of the CDU, is not yet true, meaning the buffer keeps running until three items have been counted. And for the round 2, the round 2 controls the entry configure, or it's called entry conf, which stops once the done output of the input counter, or it's called cdu_in.q, becomes true. In other words, once 3 boxes have accumulated on a buffer. And the round 3 is the input counter itself, or it would its name as cdu_in. It counts up every time the entry sensor or at entry is triggered with a preset value of 3, and it resets through the reset input of the output counter, which is called cdu_out.reset. So once the output counter finishes its cycles, the input counter becomes ready to count again. And for the round 4 is where the output counter, or it's called cdu_out, which counts item detected by the access sensors, or its name here is at access, also set to a preset value of 3, and resets itself once its own down output, which is cdu_out.q, becomes true. This is what triggers the transfer of the 3 boxes out of the buffer configure. So together, these 4 rungs create the exact queuing behavior required. The entry configure feeds boxes one by one, and the buffer configure holds them until 3 are collected, and only then does it release all 3 toward the access sensor. The next slide is to configure the Ethernet network. So it's like a controller network configuration. In here, I configured the Ethernet network for the Modicon M241 controller. I use a fixed IP address that is 192.168 and 0.110 and 0.2 and 0, with a submax 255.255.255.0. I also activate the discovery protocol, machine export protocol, and this is the important one, Modbus protocol, and the web server, which are needed so the controller can communicate with the factory I/O over the Modbus TCP. This is also have been done before in our practice module. If I am not wrong, it's in our 8th practicum. And just like when I set up the IP address on my PC earlier on, I also made sure the Windows firewall on my computer wasn't blocked the connection to the PLC. This matters because if the fire blocks the traffic, the PC and the factory I/O won't be able to reach the controller at all, even if the IP addresses are configured correctly. The next slide is for like the network configuration verification, because after downloading the program to the controller, I compared the configured parameters on the left side with the actual current settings on the right side to confirm the IP address, subnet max, and active protocols match exactly what is needed. This step verifies that the controller is properly connected and ready to communicate. Here is a quick note: if factory I/O or the PC cannot connect it to the PLC, the most common cause is a mismatch IP address. This actually happened to me once, where my PLC ended up with different IP than what I had configured, so the connection kept falling and until I checked that and matched the address again. And here, so if you run into a connection issue, perhaps you could check that first. The next slide is for Modbus TCP IP communication setup. This slide details the Modbus I/O configuration, and I want to explain why each parameter is set the way it is. This is the host where we put the IP address 192.168.10.20 with port 52502. This is matched in the PLC's IP address before, since the PLC acts as the Modbus server, and for the port 502 is simply the industry standard default for Modbus TCP. The second one is why I choose coils instead of discrete inputs, because coils are read the sensor states into the PLC's memory, and also read the actuator commands back, where the discrete input are read only, so they wouldn't let factory I/O push sensor data in at all. And also there is digital input, where the offset set as 0 and count 0. This is the range for the two conveyor motors, the buffer and the entry conveyor, since there are the outputs of the PLC sense command through, starting right from coil 0. And then there is a digital inputs, where the offsets set as 2 and count set as 2 also. This is the range for the two sensors, which we have like add entry and add exit, placed right after the output, starting coil at coil 2, since I have two output coils before it. And there is a register inputs and register outputs. Both are 0, since this project only uses simple on-off digital signals. There is no analog data to read or write, so these are left empty. And the next slide is for our integration with factory I/O simulation. This is the factory I/O driver window, where all of that configuration actually gets mapped into the sensors and actuators in the scene. Let me break it down, the full mapping. So in here, we're going to choose the driver type is as Modbus TCP or IP client, and there is a server that we have been here, that we have set before, that is 192.168.10.20 with port 502 and slave ID 1. And then we have add entry as the sensor that get mapped into the coil 2, and then add exit as the sensor also that map to the coil 3. Also the buffer conveyor as the actuator that map to the coil 1, and entry conveyor as the actuator that map to the coil 1. So this mapping basically the bridge. It connects the physical objects in the factory I/O scene directly to the variables that has been declared earlier in the PLC program using the exact offset I just explained. So here it is, our variables that have been declared inside the variable table in the SR main program. There is an add entry, buffer, CDU in, CDU out, add exit, and entry conveyor. In total, there are 4 of these that are simple bool signals with fixed I/O addresses, and 2 of them is CDU, which is CDU in and CDU out. And we have a ladder logic. So it's basically a one horizontal line of logic, like a single rule. It says if this condition are true, then run this output. So in this we have 4 rungs, and each of them has a buffer entry conveyor, CDU in, and CDU out. This is a controller network configuration where we configured the Ethernet network for the Modicon M241 controller with our fixed IP address, and also the activated discovery protocol, mission expert protocol, Modbus server, and the web server, along with the side-by-side comparison between the current settings and what we have been compared before. Do not forget to ping the IP address to make sure it's connected before we run into our configuration in Factory IO. This is the Modbus TCP or IP communication setup in Factory IO, where we configure the host port with digital inputs, digital outputs, register inputs, and register outputs. This is the Factory IO driver window where all of that configuration actually gets mapped to the sensors and actuators in this scene. There are driver type, server, at entry, at exit, buffer conveyor, entry conveyor, and any other thing else. This is the result of all of our runs and process that has been explained before, and let me explain you all over again. Now, on the left side, we have a Machine Expert Logic Builder open with the ladder program. On the right side, there is a Factory IO running the queue of item scene. On the device tree, as you can see, my controller shows a green icon and run status, meaning it's connected and my program is actively running on the actual hardware. On the factory's IO side, the connection indicator in the bottom right confirms Modbus TCP or IP client is active and communicating with the PLC. This is an online monitoring mode on the ladder diagram. So any element that turns blue is currently true and anything left black or white is false. Let me explain it to you. As items pass the entry sensor, watch at entry turn blue each time. The buffer coil stays active and CDU underscore ins CV climb one by one. 1, 2, 3. Every time the bus pass. The moment it hits 3, the CDU underscore in dot Q goes through, and you can see both entry conveyor and buffer switch off together on the screen, exactly as rung 1 and 2 describe. Then, as the 3 buses pass the exit sensor, CDU underscore outs CV or current value climbs the same way, and once it's also reached 3 from 0, its Q output reset CDU underscore in through the CDU underscore out dot reset connection, and the whole cycle is ready to repeat. So now you're seeing is the logic from the ladder diagram slide playing live and synchronized with the physical simulation. To summarize the testing, when an item arrives at the entry sensor, the entry conveyor moves onto the buffer conveyor. The buffer keeps collecting items until the input counter reaches 3. Once 3 items are buffered, the entry conveyor stops and the buffer conveyor releases all the 3 items toward the exit sensor. When the output counter also reaches 3, the buffer conveyor stops and the whole cycle resets, ready to queue the next batch. This confirms the program works exactly according to required flowchart. And that's all from me. I hope I could explain you with all my best. I deeply apologize if there is anything wrong that I said before or whatever I have been explaining before. Thank you for watching. Wassalamualaikum warahmatullahi wabarakatuh.